The objective of this video is to demonstrate how to perform a multiple linear regression analysis. The example we're going to use contains 16 observations on the viscosity of a polymer and two process variables, one being reaction temperature, the other catalyst feed rate, as shown below. We're going to evaluate the model to an alpha equal 0.05 or a 95% confidence level. First thing I did is I wanted to plot each of the independent variables against the dependent variable, and if you look at both charts here, they both look to be linear trends. So the first thing we need to do is get our data, and so we're going to perform the multiple linear regression using the data analysis tool pack. So we're going to hit data, data analysis, click OK, and I will clear some fields here. So for the Y range, we're going to put in this column of data. For the X range, we are going to capture both columns of data here. I check labels because we have labels. Confidence level 95%. I'm going to put the output range right here. Check residuals and click OK. And so now we have all of our data below. We have all of our correlation coefficient, adjusted R squared, standard deviation, or excuse me, standard error, and our ANOVA analysis, and all this other information that you're used to seeing. So I'm going to switch to the next page in order to walk through the process of how to analyze this data. Step one, we use the global F test, which is in the ANOVA section of the output, to conduct what's called the overall adequacy of the model check. So the null hypothesis is that all of the betas, beta 1, beta 2, these are the different slopes down here, equal 0. That is the null hypothesis. The alternative hypothesis is at least one beta is not 0. Now the statistic we use to make this check is we use the F statistic right here, and then we're going to, in order to calculate the p-value to establish if we reject it or not reject it, we're going to use f.dis.rt, and the value that you get is a very, very small p, much, much less than 0.05. So we are going to reject the null hypothesis, which says at least one of our slopes is not 0. The key thing, if you do not reject this test, just stop. The model is not effective and you need to go fit a better model. In this case, we do reject it and we're going to move forward. Step two, now we go and check each of the individual slopes against their respective t statistics and find that, again, our p-values are much less than 0.05, and our confidence intervals for both x1 and x2 do not go through 0, so they just add emphasis that our slopes are indeed good predictors. Step three, we come up here to this part of the summary output and we examine our correlation coefficient, and we see it's highly linear, which means we have a strong linear correlation. And you saw the charts, both variables, feed rate and temperature, both are linear against viscosity. Our adjusted R squared, 91.6% of viscosity is explained by catalyst feed rate and temperature, so that's all good. We do our 2S check, so we multiply standard error times 2, we get 32.7. We come down and check it against all these residuals and find that they're all within 32.7. So this is telling us that we have a good model. So In summary, between step 1, the global f-test, step 2, the individual t-test against each individual slope, and all these other parameters show that we have a good model that we can now use for estimation and prediction. Next step, we're going to find the least squares regression line. So y hat is equal to 7.62 times x1 plus 8.58 times x2 plus the intercept 1566.08. Now, as an example, I've chosen a value for x1 and x2. Both are within the range of the observations, and let me go over to that. I chose x1 of 92, fits well within this range, and a catalyst feed rate of 10.5. And so if I come back here, what I've done is I have substituted the values for x1 and x2 in this equation. I'm just going to add this 0.08 for completeness. And for x1 of 92, x2 of 10.5, my y hat is 2357.21. Step 5, I now want to calculate a 95% prediction interval. And so in order to do that, I need to find my margin of error. And so my components for the margin of error is my T alpha 2, my standard error, and I'm going to add a 1.1 multiplication factor on the product of T alpha over 2 times standard error. This is a very complicated analysis to get what this multiplying factor is. 1.1 is accepted practice, so that's what we're going to use. So T alpha over 2, we use the T dot inverse dot T 2T command, 05 for the alpha level, and 13 is our degree of freedom. We use the value in the ANOVA table right here that corresponds to the residual line. And that gives us that. Our standard error, we just pull from right here, cell D10, and multiply those two, multiplied by 1.1, and our margin of error is this 38.87 number. So our lower bound for our prediction interval is equal to this y hat minus our margin of error, and our y hat plus the margin of error, and we now have our 95% prediction interval, and I'll go ahead and reduce that to 2 significant digits. And so our prediction interval, 95%, goes from 2318 to 2396. That concludes this video.